Okay, so now I want to describe a solution to these equations, which we're gonna do the full mathematics of a little bit later, but I'm going to describe what it looks like. So first of all, let's look at the equations for a second. And this first equation now, the right-hand side is just 0. So Gauss's law has become just as boring as magnetic Gauss's law. And in fact, all these two equations tell us in vacuum is that there are no charges and there are no magnetic monopoles. And there's not much more to say about them. So the whole game now is Faraday and Ampere Maxwell. And notice actually that it's Maxwell, not Ampere anymore, because the term I've crossed out here was the one that Ampere discovered. And we've just crossed that out because there are no currents. So I now have an equation that relates E to the time derivative of B and B to the time derivative of E. So we're going to make some particular choices that will simplify the solution. And the first choice we're going to make is I'm going to choose that I'm going to describe to you a solution in which there's a wave that's going that way. And we're going to call this direction the x direction. So we're going to have a wave that's propagating in the x direction. And it will be a wave in which not all components of the electric and magnetic field are non-zero. In fact, it's going to be a wave in which Ex and Ez are 0, but Ey is not 0. And it will be a wave in which Bx and By are 0, but Bz is not 0. And furthermore, these two non-zero components of the electric and magnetic fields are going to have the feature in this solution that Ey is independent of either x, that Ey is independent of y and z. And same for Bz. Bz is independent of y and z. So we're going to be looking for solutions to these equations in which the things which are non-zero are Ey, and Ey is going to depend on x and time, and Bz. And Bz is going to depend on x and time. Now, how did I get these choices? Well, I got these choices because I know where we're going. I don't want to begin by describing the most complicated solution to these equations. I want to describe a simple solution to these equations that will show you that there's waves here. And so for me to make these choices, it's true I had to know where we're going. So you can think of this as me saying, I will convince you that there are solutions to these equations with these properties. And so I still have to convince you. You have to wait till we actually get there to be convinced that I can find solutions with these properties, but I can. So there are two non-zero quantities, two non-zero functions of x and time, Ey and Bz. And let's just imagine what they might look like. So I might find a solution in which Ey as a function of position x, so this is Ey at one time, might have some interesting shape to it. Might look like this. And then Bz at one time, the same time, as a function of x, might also have some interesting shape to it. And in fact, we're going to see that they will have the same interesting shape. I could have picked any interesting shape here, but what we're going to see is that I then need to pick the same interesting shape here. And so we're going to be looking at graphs like this. We're going to be depicting graphs like this. But before we go there, I want to pause and make sure that you understand what a graph like this is actually saying. To understand this graph, you have to have internalized everything that I said up here. And in particular, you have to remember that EY is independent of Y and Z. What does that mean? Well, so that's the x direction. And this says that in the x direction, EY, well, here it's 0, and then here it's positive, and then here it's 0, and here it's negative. Okay, you can read the graph. But remember that this is telling you the value of EY, not just along one line like this, but along any axis in the x direction, whether it's here or here or here or here, because the value of EY is completely independent of Y and Z, which means that the fact that EY is positive at this value of x, what it's telling you is that on an entire plane, okay, there's an entire plane in a YZ plane at this value of x. And on this entire plane, EY has this positive value. And on the same plane that we were just talking about, because it's at the same value of x, BZ has whatever this value is. Then you go to a different plane a little bit over in x. And on this plane, okay, right here at this value of x, EY is negative and BZ is negative. So these waves that we're describing are called plane waves. So the solutions that we are talking about are plane wave solutions to what? To the vacuum Maxwell equations. That's what we're describing. And then the last step is to say, well, what happens as time progresses? This is what happens at one time. And what we are going to see is that these equations don't describe a solution like this standing still. There's no such, so if I said I have this EY, this BZ, and they're standing still, they're independent of time, you can run through these equations and you will quickly convince yourself that that does not satisfy these equations. That is not a solution to Maxwell's equations. What we're going to see is that these are solutions to Maxwell's equations if they're moving. That way, in fact, for the solution that I'm going to construct. So this pattern of EY is moving to the right, and this pattern of BZ is moving to the right. So the plane where EY and BZ are positive, which is here at this time, a little later it's over here, a little later it's over here, a little later it's over there. So you have this rolling wave of sort of planes of places where EY is positive, separated by planes of places where EY and BZ are negative. So this whole pattern moves this way, okay, as time progresses. So that's a qualitative description of the solution that we're about to find. So what I need to do now is I need to show you how to find solutions to Faraday and Ampere-Maxwell, emphasis on the Maxwell because Ampere's term is gone. So Ampere-Maxwell, mostly Maxwell. These two equations, I need to show you how to solve them for these and find out what these equations tell us must be the case about these two functions, EY and BZ, always keeping in mind that EX and EZ and BX and BY are all 0, and that EY and BZ are independent of Y and Z, meaning that what we're describing are plane wave solutions. And that's where we're going. And we'll start by showing how to solve Ampere-Maxwell, and then we'll show how to solve Faraday, and then we'll put it all together, and we'll see what it tells us about these solutions.